Yeah, I'm really excited to be with you all. And it was neat. I think I heard at least one new PhD student who's working in explainable AI. So it's always neat. Cool to hear new students getting into the space. So today I'll be talking about some of our work in interpretability, or it's also known as explainable AI. And I'm going to have a particular focus on new directions as we enter the second decade of deep learning. So this might be a bit of a refresher for most of you, but interpretability just refers to any research that focuses on explaining complex AI systems in a human interpretable way. This is particularly relevant in the past decade as deep neural networks have kind of overtaken machine learning and a lot of the application areas, but these models are really complex. They're composed of millions to billions and now even trillions of parameters, and thus they're really difficult to understand. There's a few different reasons why we need interpretability. One motivation for this line of work is a scientific curiosity to understand these complex models. And this is somewhat analogous to how neuroscientists study the human brain. And the second is to engender trust in AI systems. So for this, you can consider AI-assisted medical diagnosis, where a doctor may want explanations of how an AI system made a certain prediction in order to decide whether to trust or use that system for that prediction. And the third, which I think hasn't been built out as much, but is probably going to become increasingly a motivation, is for us to be able to learn from these AI systems themselves. So you can consider AlphaGo from DeepMind, which surpassed expert human abilities in playing the game of Go. And now human players often study AlphaGo games to try to improve their own gameplay. And you can imagine that if we had explanations of AlphaGo decisions, this could really help facilitate that learning process. There's also other considerations, for instance, legal regulation. So where you guys are in the European Union, the GDPR, the General Data Protection Regulation, enumerated a right to an explanation for algorithmic decisions. How exactly we provide these explanations is still to be discovered. So as you can imagine, these are really different motivations. And it naturally follows that explanations may look very different depending on the reason for interpretability. And we're going to discuss some of that resulting diversity. Before looking forward to the next decade of exciting research directions, I'll give a very brief retrospective on the first decade of deep learning and interpretability. So in deep learning, there have been a number of exciting developments, starting in 2012, when AlexNet and ImageNet together demonstrated the power of convolutional neural nets when given enough training data and the right hardware, to more recent progress in generative modeling. First with GANs, and more recently with diffusion models like DALL-E 2 and Imagine. We've also seen more crosstalk between adjacent communities like multimodal self-supervised learning and transformers making large gains in NLP and now computer vision. These are just a few of the many exciting movements within our research communities. And ideally, we hope that interpretability moves with the broader community as new frontiers are being explored. So how do we do in the past decade? In interpretability, there have been three main dominant research areas. The first has been focused on explaining why a model made a specific output prediction. From this research theme, attribution heat maps, which visualize where a model looks for evidence in an input for its decision, arose and became the most research area within interpretability. The second major focus has been on understanding the internal workings of deep neural networks. In this theme, researchers most actively developed various quote-unquote feature visualizations that showed the visual stimuli that most activated individual channels in a network. It's important to note that both of these approaches primarily explained and studied existing models post hoc, meaning after they've already been trained. The third and most recent development has been on developing models that build in an explanation as part of its decision-making process. And these are known as interpretable by design models. So how do these three major themes in interpretability map onto the major research directions in deep learning? It turns out not too well in terms of coverage. You'll note that these works primarily focus on understanding and approximating CNN, typically image classifiers. There were a few exceptions like GAN-paint and transformer circuits that focused on understanding GANs and transformers respectively. That said, on average, most interpretability work didn't extend beyond CNN classifiers. So when I think about the next decade of interpretability, kind of two goals come to mind. The first is we want to develop interpretability methods for diverse domains. We need to move beyond just CNN classifiers and develop interpretability for a wide range of research that is represented in our research communities. And the second is we really want to center humans throughout the development process. Specifically, when we're developing these methods for engendering trust, we need to have real-world stakeholders at the table and understand their unique interpretability needs. Currently, most existing work isn't suitable to be used in the real world. Also in evaluation, we want to be critically measuring the human interpretability and actual usefulness of our methods. And finally, in deployment, we want to be able to package these tools so that they can be easily used and adapted by the wider community. So for the rest of the talk, I'll be discussing 4 recent works that kind of move in some of these new directions and flesh them out. And I'm also going to highlight along the way some current challenges to developing new work with those 2 goals in mind. So first, I'll discuss our recent work, HEIBRIDS, on evaluating the human interpretability of visual explanations. And in this work, we move from automated evaluations of interpretability towards more human-centered evaluation via human studies. And this project was led by Princeton PhD student Sunny S.Y. Kim. So here we're primarily focused on explanations that answer the question, why did a model predict a specific output class? And there's a few different ways explanations can be formed in order to answer this question. So most of us have probably seen these attribution heat maps. This is kind of the most actively developed explanation form factor, but there's actually a number of other kinds of explanations that can answer this question. For instance, concept-based approaches explain a model's prediction by the presence or absence of interpretable semantic concepts. For instance, to explain the prediction of this particular bird species, a concept-based explanation would note that there's the presence of black wings and maybe a yellow kind of head. Another class of explanations is what's known as prototype-based or patch-based explanations. And here, a model's prediction is explained by using some canonical image patches that are known as prototypes, and then matching patches within the input image to these prototypes and kind of doing a similarity, summing over the similarity scores with these prototypes. And finally, there's a few others, and I won't go into all of them, but another one is known as counterfactual explanations. And here they actually answer a slightly different question of why did the model predict one class over another? So ideally, we'd like an evaluation framework that allows us to compare and contrast the usefulness of all kinds of explanations across these different form factors. And just one other axis of variation to discuss is how our explanation is produced. So most research has been in developing what's known as post hoc interpretability methods, meaning explanations that explain a model after it's been trained, meaning that the explanation was not part of the original model's design. And as I mentioned before, more recently, interpretable by design models are ones that are designed such that they produce and use an explanation as part of the model's decision-making process. So similarly, we want to be able to compare both post hoc and interpretable by design methods in evaluation. So what's the state of evaluating explanations these days? Most current metrics focus on explaining just one kind of explanation, namely post hoc attribution heat maps, and most are automated evaluation metrics. They also primarily focus on verifying the faithfulness of an explanation. That is, whether an explanation is specific to the output neuron or output class or model parameters that are being explained. To our knowledge, there has been no human evaluation metric that allows for diverse cross-method comparison. And our work really focused on evaluating the human interpretability and usefulness of these kinds of explanations. So in HEIBRIDS, we had 3 main goals. First, we want to enable cross-method comparison and contrast the prior works that primarily evaluated heat maps. Second, we want to center humans in the evaluation process and measure if these techniques are actually useful for humans and contrast the prior works that primarily focused on measuring faithfulness through automated means. And third, we want to enable falsifiable hypothesis testing. And this is in contrast to some intuition-based reasoning that led our community astray in the first few years of heat map development. And a really good example of this is the sanity checks paper by Adebayo et al. In NeurIPS 2018, where they showed that if you randomize a model's parameters and generate heat maps, you actually get very visually similar heat maps. And what that shows is that these heat maps weren't actually explaining the particular model parameters, but probably capturing something more simplistic as like image content or kind of edges. So it's really important that we have rigorous falsifiable hypothesis testing built into our evaluation. And we're not just looking at these explanations and saying, this seems to make sense, and basing it off just human reasoning. So our contributions are as follows. We present a novel human study that evaluates 4 interpretive methods across different form factors. And in particular, we're the first human study for evaluating interpretable by design and prototype-based methods. Our study quantifies the usefulness of explanations in distinguishing between correct and incorrect predictions. And we also interrogate how users are willing to trade off between interpretability and accuracy of the model. And finally, we open sourced our HEIBRIDS studies to encourage more reproducible research. So first, in our initial study, we focus on evaluating 4 diverse methods: GradCam, BagNet, ProtoPNet, and ProtoTree. And these techniques span both heat map and prototype-based methods, as well as post hoc and interpretable by design techniques. In our initial study, we had 2 tasks. On the left, the agreement task measured how confident a participant was in a model's prediction, given an explanation for a single prediction. In our distinction task on our right, we measured our participants' ability to distinguish which is the correct class, given several explanations for different output classes. And for each of these studies of a particular explanation and a specific task, we recruited 50 participants through Amazon Mechanical Turk. I'm going to now explain the tasks in a bit more depth, and I'm also going to highlight a few of our key findings along the way. So here's a condensed UI for the agreement task, which asks the participants to rate their confidence in a model's prediction by answering this question. You'll notice that for prototype-based explanations, we also include a similarity rating subtask in both the agreement and distinction tasks that asks participants to rate how similar an image patch is to a given prototype. This ensures that participants looked at and understood the prototype explanations, which on average were more complex than the heat map explanations. And our first finding was that these computed prototype similarities by the model often did not align with human notions of similarity. And when we looked at participants' ratings of prototype similarities, we found no significant correlation between their ratings and the model's computed similarity scores. So in terms of ensuring that these models are kind of intuitive and follow human notions of interpretability, this is kind of one example where if we're relying on prototype similarities to be like how humans reason, we still have a long ways to go. And our study confirms some anecdotal observations made by previous works that these prototype similarities didn't line up with human notions of similarity. Our second finding is that the agreement task reveals confirmation bias. So when we analyze participants' response to this question boxed in blue, we found that more than 50% responded that they were either fairly or somewhat confident that a prediction is correct. And this was true even when incorrect predictions were shown. So in reality, what we wanted to see is that when they were given an explanation for an incorrect prediction, that the percentage that rated that they were fairly or somewhat confident that this prediction was correct should be lower than 50%. But we saw that it was still higher than 50%, which signals that kind of these explanations are giving a false sense of confidence in the model's prediction, which is not what we want. So moving to our distinction task, here's an example of our UI. And here, participants are asked to select which of 4 classes is correct based on explanations for different output classes. And when we analyze responses to this first question, our third finding is that participants really struggle to identify the correct class, especially for incorrect predictions. So for heat map explanations, we saw that they correctly answered this question around 25% of the time, which is the same as kind of the baseline of just randomly guessing one of these 4 classes. And this shows that our explanations aren't really useful for helping users distinguish what is the correct class. And here, this kind of motivates what we think is a goal, one of the goals for interpretability in these cases. is that interpretability should help humans identify and explain model errors. And our work shows that we still have a long way to go for this to actually be true. Finally, the third goal was to enable falsifiable hypothesis testing. And our key findings are examples of that, where we test and either validate or reject hypotheses about explanations. For instance, we tested the hypothesis that prototype similarities match human notions of similarity, and we're able to reject that hypothesis. At the end of the study, we asked participants to specify on a sliding scale how much more accuracy they would require a baseline model with no explanations to have over a model with explanations. And we asked participants to answer this question for 3 risk settings. First, for low risk settings like educational uses. Second, for medium risk settings such as biodiversity monitoring. And lastly, for high risk settings like veterinarian science. And here on the x-axis, we show the risk setting, and on the y-axis, we report the mean required accuracy gain a baseline model needed to have over a model with explanations in order for participants to prefer that baseline model. For high-risk settings, participants required a baseline model to have almost 11% higher accuracy over a model with explanation. And what we found was somewhat surprising to us, that as the risk setting increased, participants actually wanted higher accuracy from the black box baseline model, which we thought it might be the reverse, that in high-risk settings, they might be willing to sacrifice explanations so that they can get a better performance accuracy. So now I'm just going to briefly mention some of our follow-up work on a slide. So here we kind of move from Amazon Mechanical Turk studies, which are really a kind of survey-based studies, to an interview study. And here we wanted to understand kind of real-world interpretability needs for a specific ML context. So we conducted 1-hour-long semi-structured interviews with 20 users of the Merlin app. And this is a popular birding app that recognizes different bird species from photos uploaded by users. And one of the many questions we studied was what kind of explanations did participants prefer? So we showed 4 mock-ups of different explanation form factors, heat map-based explanation, prototype, and concept-based explanations, as well as example-based explanations. And what we found through our interviews in discussion with participants is that they preferred prototype and concept-based explanations, primarily because they were similar to how participants themselves reasoned about recognizing birds. For instance, they often noted that they recognize birds by kind of noting specific parts and kind of summing up our kind of collecting together that evidence of the presence of specific parts, which is similar to how prototype-based and concept-based explanations work. So for more details, please check out our preprint on this. Zooming out, we identified a few challenges for future human evaluation work. First, there's a skills cost to human studies. That is, you need to be able to develop these UIs and have strong web development skills, which is not always the case for AI ML researchers. The second is a financial cost in budgeting for participants' pay. And the third is a time cost in designing and iterating on these studies. And in addition to iterating on the UI, this includes ensuring that tasks are feasible for participants, getting IRB approval, and incorporating quality control measures. However, given that all these motivations for interpretability involve humans being able to use explanations effectively in some way, our evaluation of these methods need to be human-centered. Thus, one key takeaway is that as a research community, we need to invest in and reward human evaluation studies, just as we do for data set development, which has been crucial for progress in our field. And this is similar to how we budget for GPUs and cloud compute. We want to be budgeting for human evaluation. So I just wanted to check, did we want to take questions all at the end, or did we want to stop kind of after each major component?
Are there questions at the moment from the room? So maybe we take them for the end.
Okay, sounds good. Great. So next, I'll be discussing our work on Elude, on generating interpretable explanations via a decomposition of labeled and unlabeled features. So here, we're focusing on concept-based explanations, and we're moving from explanations that use only labeled semantic concepts to explain model decisions, using both labeled concepts and unlabeled features. And this project was led by Princeton PhD student Vikram V. Ramaswamy. So for some background, concept-based explanations aim to answer the question, why did a model predict a specific class? And they do this by explaining a prediction via the presence and absence of labeled semantic attributes. For instance, a concept-based explanation might explain that this model predicts sheepdog because fur and paw are present in the image, but trees aren't. And the main benefit to this approach is that these labeled concepts are interpretable to humans. We can reason about the presence of fur and paw. So one example of concept-based explanations is the concept bottleneck model introduced by Ko, Win, and Tang et al. In ICML 2020. This interpretable by design model predicts the presence and absence of attributes and then learns to weight the importance of each attribute for the output class. And it does this by linearly combining everything to form its output prediction. However, there's several problems with this approach, primarily because they're using these fractional values or continuous values, which can be really hard for humans to reason about. And second, they can encode hidden information. For instance, when the original authors passed this absence and presence vector through a sigmoid function, effectively binarizing the fractional values, they noticed that the performance dropped significantly, suggesting that these kind of fractional values were encoding some other information that the model was able to use. So kind of building off of concept bottleneck, our latest work differs in several ways. And first, our goal is to approximate the behavior of a model after it's been trained. So this is a post hoc technique, instead of training an interpretable by design model from scratch. And second, we do this by explaining the model's behavior as a decomposition of both labeled attributes and unlabeled features. So how we do this is first, we learn how to make predictions by linearly combining ground truth attributions for an input image. So you'll note that here our indicator vector is binary and not fractional. So this is easier for humans to reason about. And after we've explained as much as the model using these labeled attributes, we then learn a remaining unlabeled set of features as a low rank space. And now we can analyze what can be learned using these semantic attributes alone and what has yet to be discovered in this unlabeled feature space. So looking at explanations via just the labeled attributes for 3 scene prediction tasks of increasing complexity, we're able to quantify how well these attributes explain the original model. That is, how well they match the original model's prediction. And we find that as the task complexity increases, the amount that labeled attributes can explain the original model's prediction decreases. And this kind of highlights some of the problems with using those continuous fractional values instead of binary attributes. And that is, they can encode hidden information. And this is one of the limits. And kind of more broader, this is a limit to attribute-only approaches, that they can't explain a model 100%. Something is always left on the table. So if we dive a little bit deeper and we analyze a 16-way kind of coarse-grained scene group classifier, we can kind of break down performance for each output layer. And here we're showing the true positivity rate for predicting each label as the model did. And you'll notice at the top that for some scene groups like home or hotel, this can almost be entirely explained using labeled attributes alone. But at the bottom, there's about half a dozen scene groups that can't be explained at all using just attributes. And this suggests that perhaps the attributes that we were using were more relevant for explaining certain groups over others. So now to kind of understand what we're missing in our set of attributes, we're going to start analyzing that low rank feature space. So here in each row, we're showing a few maximally or minimally activating images for directions from rank 4 feature space for predicting our 16 scene groups. And you'll notice that these are really semantically coherent. And now when we kind of look back to the table on the prior slide for the performance per scene group when using attributes alone, we notice that some of these directions from the low rank feature space map on pretty well to some scene groups that weren't able to be explained using just attributes. For instance, bowling alleys is an indoor sports or leisure scene, and both indoor sports and outdoor fields were poorly explained by attributes alone. And this suggests that by understanding this feature space, This is a key to understanding what still needs to be explained by concept-based methods. And our work can be viewed as a recursive decomposition, where we can imagine discovering new attributes that should be labeled and included in our concept set from this low-rank feature space, and slowly reduce the quote-unquote remainder that is not explained using attributes alone. So we recognize that using attributes is really powerful, but in order to kind of improve the quality of our concept-based explanations, we kind of need to be discovering what concepts we need to be adding to that set to form better explanations. So in some follow-up work, we kind of zoom out and investigate several important factors for concept-based explanations that have been overlooked in the literature so far. And I'll just briefly highlight 3 of them. The first factor is the choice of the probe set matters. That is, the probe set is the data set with labeled concepts. And we found that using different probe sets result in very different concept-based explanations for the same output class. So for instance, suppose we're trying to construct an explanation for why a model predicts the scene hockey arena. And when we use one probe set, the learned explanation uses concepts like grandstand, goal, ice rink, and scoreboard. However, when we use a different probe set, the learned explanation uses a completely different set of concepts like plaything and road. And here, our point is that probe data sets should be chosen with a deliberation and caution. And we suggest that you should choose a probe set with as similar of a distribution as possible to the underlying training data set with which the model was trained. The second factor is a little bit more subtle, and that's that some concepts used in explanations are harder to learn than the output classes they're trying to explain. This is in part because the choice of concepts used in explanations is dependent on the available concepts labeled in the probe set. So for instance, let's say we're trying to train a model. Let's say we learn a model to learn the output class bathroom, and it achieves a normalized average precision of around 43. Now when we kind of similarly train a model to learn the concepts used to explain that bathroom prediction, so the concepts toilet, shower, countertop, bathtub, and screen door, the normalized AP for learning these concepts is all lower. That is, the output class bathroom is easier to learn than the concepts used to explain it. And we argue that this is somewhat problematic because what we really hope for concept-based explanations is that these kind of concepts are building blocks, or simpler building blocks that kind of help form a more complex output like a scene. So if they're harder to learn than the actual output, this suggests that they're not actually part of the model's decision-making process. So one immediate takeaway we have is that we should only use easily learnable concepts in our explanations. And kind of a longer term or harder takeaway is that we want to be able to develop more causal approaches to concept-based explanations to really ensure that these concepts were the way that a model made its prediction for a certain output class. Finally, the third factor is that participants can only reason about a small number of concepts, and we find that the upper bound for this is around 32 concepts. However, most current concept-based explanations use hundreds of concepts in their explanations. So to study this, we ran an Amazon Mechanical Turk human study with 125 participants, where we first asked participants to select the presence of different concepts in these checkboxes. And we varied the number of concepts shown from 4 to all the way to 64 concepts. And then we showed them explanations for 4 different scene predictions. And here we're only showing one explanation for scene W. Then we asked participants 2 questions. First, based on these 4 explanations, which of the 4 scenes do you think the model predicted? And then after doing this study, secondly, how many concepts would you prefer to be used in the explanations? And here, this is how we kind of get that upper bound of 32. In addition to identifying this upper bound, we found that participants really struggled to identify the presence of concepts as the number of concepts in that list increased. So when there were only 8 concepts in the list, they had an accuracy of identifying concepts with around 72%. But when there were more concepts like 32, they're actually decreased to around 57%. And this kind of highlights the need to design our explanations to accommodate human limitations, such as cognitive load. So zooming out a bit, some of the challenges for concept-based methods is that attribute-only approaches are incomplete. And we need to recognize that whenever we're developing this class of methods, that any predefined set of concepts in a probe data set won't necessarily kind of capture all the potential concepts that are used by a model. Second, we want to be able to develop more methods that explain this remainder. And there's been some initial work on this, but much more work is needed. And third, we want to ensure that concept-based explanations are really human interpretable. And we notice that some explanations are using many more concepts than what humans are actually able to reason with. And this kind of also ties in with our first work, 5, where we want to be critically evaluating the interpretability of concept-based methods. So one key takeaway from all of this is that we need to be realistic about the benefits and limitations of an interpretability method and work towards meaningfully addressing those limitations. So next, I'll discuss our NERPS 2020 work on quantifying the learnability and describability of visual concepts emerging in representation learning. And in this work, we moved from focusing on understanding supervised models to understanding self-supervised models. And this work was led by Oxford postdoc, Dr. Iro Lena. And afterwards, I'll also briefly talk about expanding interpretability beyond traditional machine learning and computer vision domains. So recall that supervised learning, we're trying to predict labels Y from inputs X. And in self-supervised learning, we don't have labels. So we can only learn from our inputs, which are typically images or videos in computer vision. So what can we learn with just images? Well, we can consider the scenario where you're given some groups of images, which I'm presenting here as rows, where each group defines a visual concept. And humans can easily learn concepts from examples and then decide whether new images are instances of those concepts without ever needing labels to name these visual groupings. So for instance, we could probably match these new query images to the groups they most likely belong to. So recently, self-supervised algorithms have reached and even surpassed supervised pre-training on ImageNet for downstream tasks. However, as we mentioned at the very beginning, most interpretability research has focused on supervised learning, specifically CNN image classifiers. And here we argue that we need to develop a deeper understanding about the representations learned by self-supervised methods as they're becoming increasingly more prominent in our research community. In this work, we asked the question, to what extent are these methods able to discover human interpretable concepts? So our goal is to provide a quantification for the visual interpretation of emerging image groups from these self-supervised methods. And right now, there's 2 main trends for obtaining these groupings. The first is to jointly learn representations and pseudo labels, which directly yield a set of clusters. And the second is to apply a clustering algorithm like k-means offline on top of learned representations. So here we propose 2 measures based on human judgments. The first is learnability. And here we want to check whether a visual grouping is interpretable and coherent. And we measure this by testing the ability of human participants to discriminate new instances of a group from negative ones in a forced binary choice setting. So here the ground truth is determined by the self-supervised method that is being evaluated. And most of us can probably answer this, that the correct answer is A. Furthermore, we probably can also describe the grouping on the left succinctly with language. I might describe this as a cluster of white animals in snow. However, being able to learn patterns from images does not necessarily mean we're always able to describe them with words. So this leads us to our next metric, which we call describability. Here, instead of showing a set of images as a reference set, we try to summarize that group with a short description in natural language. And the reasoning here is if humans can accurately predict which image fits this description, then the group is not only interpretable, but also describable. In this example, you can probably guess that the correct answer is B. So we conduct experiments with descriptions provided manually by humans, but we also want to answer the question, to what extent can these groups be automatically described? And to that end, we also evaluate a group level captioning algorithm. And we conduct our evaluation on Amazon Mechanical Turk using clusters from 2 then recent self-supervised methods, Sela and Moko. measuring the human accuracy on those two tasks. So in this graph, each point represents a different cluster. On the x-axis, we plot what we call the ImageNet cluster purity for a cluster. And this metric roughly measures how correlated a cluster's content is to a single ImageNet label. For instance, a cluster with a purity of 1 exclusively contains images from a single ImageNet class. And on the y-axis, we're plotting the mean participant accuracy on our learnability task. So kind of putting this all together, this highlighted orange dot represents a MoCo cluster with low ImageNet purity. That is, it doesn't correlate well with a particular image class, yet it achieves nearly 100% in our learnability task, suggesting that even though it's not correlated well with an ImageNet class, it actually encodes a really semantically coherent concept. And we noticed that there's a sharp increase in learnability of clusters with increasing cluster purity. And when we look at kind of the same graph for our describability task, we find that clusters can be described almost as well as they could be learned from visual examples, which was a bit surprising to us. So kind of looking at a few qualitative examples, we find that not only are large portions of clusters human interpretable and semantically meaningful, this is even true for those that don't correspond well to an ImageNet class. That is, those with low ImageNet purity, which we're showing in red. These metrics aren't only limited to understanding self-supervised clusters, but they could also help us understand feature spaces. For instance, the low rank feature space from Elude. And there's also some follow-up work which uses concept pseudo labels to measure the semantic coherence of self-supervised clusters. So now I'll just kind of, in this work, we kind of talked about the shift from explaining supervised models to self-supervised models. And now I'm just going to briefly explain two works on extending interpretability to even further reaching domains. So the first is our project in the machine learning fairness space on gender artifacts in visual data sets. And this project was led by Nicole Meister and Dora Zhao, who are former Princeton undergrads. So here we're interested in understanding how pervasive are gender artifacts in computer vision data sets, and we apply a variety of techniques inspired from the interpretability landscape. In this figure, we show some statistical differences between the top 20 female versus male predicted images by a model. And you'll notice some pretty surprising things. First, that the average poses are quite different. Women tend to be more centered and larger in images, and even the average color is different. And we just want to make a quick note that here, when we say gender, we didn't ask the people who are in these images what their gender identity is. This was annotated by some other annotator who was perceiving a binary gender expression. So this isn't gender identity. And what we did in this work is we learned to predict these gender labels when we were kind of perturbing an image. So we made these images low resolution. We only showed parts of the image, like just the background or just the person. We even tried only feeding in just the average RGB value, so 3 features. And basically every perturbation we tried, we were able to predict these gender labels above random chance, which signaled that these gender artifacts are everywhere in visual data sets. This is somewhat surprising because, and I think it really has serious implications for the machine learning fairness community, because a lot of their mitigation techniques are what are known as bias blind techniques. So what they try to do is they try to make a model blind to certain factors such as gender. And you can imagine training a model in an adversarial way to quote unquote erase all predictors for gender labels. But if these gender artifacts really are everywhere in visual data sets, this is really going to hamper and cripple a model. So we really think that the community should move beyond these bias blind strategies to more bias aware ones, recognizing that these kind of distribution differences are everywhere and encoded in really subtle ways in our data set. And we need to be aware of this, but not necessarily blind to that. So just one last comment is that we don't condone gender prediction. And here we're only using a gender prediction model for the purposes of analyzing gender artifacts. We're not actually interested in predicting gender, and there's a lot of ethical qualms with doing that. Second, there's been some interesting work on extending interpretability to other disciplines. And one example I'm just going to give is in the geosciences. So in one of our projects, we adapted interpretability techniques to understand and improve a coral reef fossil segmentation model. And you'll note that this is different than the typical image classifier setting that most interpretability methods have been developed for. So here we identify and mitigate several failure modes of this model. And this project was led by Princeton undergrad Indu Panagrani. And another line of work that I learned about very recently is in the climate science space from Elizabeth Barnes' group at Colorado State University. So in one project, they use attribution heat maps like a layer-wise relevance propagation to identify important regions in the world that are reliable predictors for seasonal climate indicators. And kind of in conversation with Elizabeth Barnes, as well as in our own experience working with coral reef fossils, we noticed that there are some really unique challenges when we start adapting interpretability techniques to other domains. So kind of zooming out, there's a few challenges to kind of extending interpretability to these new frontiers. And the first is kind of each domain has some unique set of interpretability needs, and we need to be developing specifically for that. It's not as simple as applying existing methods to a new domain. So for instance, most prior work has been on understanding CNN classifiers, but that setup didn't hold up for self-supervised learning. And secondly, especially in some of these newer developed areas, the lack of access to standard implementations is quite crippling. So in the early years of self-supervised learning, it was really challenging to develop interpretability simply because it was hard to reproduce self-supervised models in order to compare them. With time, this has become much better. And as we kind of look forward to, say, state-of-the-art large language models, which have legitimate safety concerns for restricting full access to model parameters, we still want to consider how we can balance these safety concerns with a more open research style, which invites further accountability from the field. So one key takeaway from all of this is that we need collaboration and buy-in from the wider community, particularly those working in diverse novel frontiers, in order to be able to effectively develop interpretability in those domains. So finally, I'll discuss some of our work on interactive similarity overlays. And in this project, we move away from static visualizations to interactive ones. So current interpretability tools typically render static visualizations. Here on the top, I'm showing some attribution heat maps, and on the bottom, I'm showing some feature visualizations. But what we were really interested in is, what if interpretability tools were interactive and leverage the full expressive power of modern web technologies? And we want to note that there are some existing interactive visualizations, but these tend to be kind of well-polished demos that aren't easily extendable to new models. So we're particularly interested in creating lightweight visualizations that can be dropped into a researcher's workflow. So we're interested in interactive visualizations because we argue that they're more human-centric. It allows humans to easily explore a model, and it's often more digestible than presenting the equivalent information via static visualizations. So in our work, we want to design tools that are interactive, exploratory, and easy to use. This is similar to a doctor's stethoscope, which allows a doctor to easily examine different body parts. In our case, we want to easily explore different hypotheses about a model. For instance, how do different layers in a network compare to one another? What about different image regions? So our first kind of visualization in this space is interactive similarity overlays. And as we're hovering over this image, we're dynamically rendering an overlay that shows how similar other image patches are to the current image patch, highlighted in yellow. And here, lighter patches are viewed more similar by the model, while darker patches are viewed less similar to the current image patch. So we do this by first I'll first go into a bit of detail on how we do this. So if we were able to, if we were to cut a network, which we call the function f of x somewhere in the middle, the first part is going to produce an intermediate output. And for models that take images as input, this intermediate output is a 3D volume. So now for every spatial location in our activation volume, this is a vector of activations where each dimension corresponds to the specific channel. So we can compute the activation vectors for all spatial locations, and then we can visualize the similarity or distances between activations at different spatial locations. So I skipped a little bit here. What we're visualizing is the theta on how, what we're visualizing is the theta as to how dark or light patches are with respect to the highlighted image patch in yellow. So I'll just briefly show some interesting examples of what you can do with our visualization. And you can actually follow along and play along with this yourself. We have an interactive article that we publish in. So in this example, we compare image patches across different images. So the current image patch in yellow is being compared to all other patches in the 6 images. And we notice a few interesting findings when we play with this. So first, when we're hovering over image features like eyes or nose, we notice that the corresponding features are highlighted in other animals. And I notice this is a little bit jumpy. This probably is because of Zoom. So you might want to play with this yourself. And the second thing we notice is that when we hover over the background regions, we notice other image backgrounds are also highlighted, despite being different colors. We can also use our visualization to explore how different layers represent image patches. So in this example, we show overlays for activations after 3 different network layers, early, mid, and late layers. And we synchronize the highlighted image patch. So note that in this example, the highlighted patch is only being compared to other patches in the same image. So only activations from the same layer. So here we notice that in the earlier layer, this tends to kind of capture more low-level details like edges, for instance, a 45-degree oriented edge here that we're seeing pop out on the head and the body of the dog. Whereas later layers kind of capture more semantic concepts like the head of the dog or its torso. Finally, in this last example, we demonstrate how you can combine our qualitative visualization with other techniques. So here on the bottom right, we're showing a line plot that plots the similarity scores of the highlighted image patch to its corresponding rotated patches in the other images. So in this particular example, when we are hovering over the dog's nose, what we're showing in the plot is the similarity score for all the other rotated dog noses in the other images. And when we combine techniques in this way, we're able to kind of combine our qualitative visualization with a quantitative plot that helps us better understand how networks behave under different geometric transformations. So you'll notice that as we hover over the dog's nose, this is a really oriented feature where the similarity score drops. But then when we kind of start hovering over the background, we see that the similarity scores all kind of shoot up across rotation, meaning that background is not a orient sensitive concept. And now when we kind of hover over the edge of the image, we notice that there was kind of this oscillating pattern that was due to zero padding and is a border effect. So our code is really easy to use and works with both PyTorch and TensorFlow and can be easily added to someone's workflow in as little as 10 to 20 lines of code. Finally, we have some follow-up work called interactive visualization feature search. And here we implement a reverse image search of sorts that allows the user to select a free-form region in an image and search for nearest neighbors in activation space for a specific model and layer. And this is in contrast to our similarity overlays, which we could only compare activations across several handpicked images. So here, when I hover over this side of our politics building at Princeton, I retrieve the most similar images in the ImageNet dataset and get these arches. And we provided code to play around with this tool. This project was led by Devin Urwick, a Princeton undergrad student, and also came out of discussions with David Bao, another interpretability researcher. So zooming out, there are a number of challenges we identified for developing visualizations like this. Again, there's a skills cost of very strong web development skills. One thing that we've been excited about is that there's a number of new platforms that make it easier to create these interactive visualization and demos using only or mostly Python, which most ML researchers are familiar with. The second is that there's a potential for misusing these interactive visualizations, just as heat map visualizations were. And so while we think these visualizations can be useful for developing intuition, we want to emphasize that any hypotheses needed to be rigorously tested via quantitative experiments. The third is that developing high quality software tooling for research often isn't rewarded in our communities. And the fourth is that there aren't really great venues for publishing this type of work. There used to be this still journal, but it went on hiatus. And right now, kind of Viz AI is the main consistent venue. But more recently, the CVPR demo track was resurrected, and this might become a more promising venue for this type of work. Finally, there's a lack of crosstalk between HCI and AI communities. And we've noted that there's some pretty cool interpretability tools coming out of the HCI space, but we're often developing interpretability somewhat separately. So one key takeaway from this is that relevant research communities should collectively invest and reward software tooling for research, particularly interactive tools. So kind of in summary, the main high-level takeaways that I think are important for considering the next decade of interpretability are as follows. And this is just a summary of what we've mentioned so far. So we want to be evaluating human studies just as we do data set development and prioritizing and budgeting for GPU compute. Second, we need to be realistic and even critical about the benefits and limitations of each kind of interpretability method and focus on meaningfully addressing those limitations. Third, we want larger buy-in and collaboration from the wider research community, especially as we want to extend interpretability to novel frontiers. And finally, we want to value software tooling for research, including interactive tools. So in the beginning, I outlined these main directions for the next decade of interpretability, and I discussed several of our works that roughly map onto different elements of these directions. So in addition to advancing interpretability to new frontiers, I think the next decade of work should focus on centering humans throughout the development process. My hope is that in 10 years, we'll have methods that are demonstrably useful to a variety of humans, from ML researchers who use interactive tools regularly just as they use TensorBoard, to doctors who use explanations to decide when to use or override an AI system in healthcare, to a novice bird watcher who uses explanations from a bird prediction model to improve their own ability to recognize birds. Along that first direction of developing interpretability beyond CNN classifiers, we hosted an ICML 2020 workshop on this topic and published a book that resulted from some of our conversations there. So in conclusion, I started off with a retrospective of the first decade of deep learning interpretability, where we were primarily focused on understanding and approximating CNNs. And I'm really excited to see what comes from the next decade. And I hope some of you here join us, even if you're new to the field or to interpretability. I find it's always useful to have more diverse minds working in this space. So lastly, none of this work would be possible without my amazing collaborators, as well as our funders. And Olga and I are hiring postdocs. So if you're interested in interpretability or ML fairness or interactive viz, we're really interested in chatting. So I think that's all I have, and I'm happy to take some questions.